Hello, everybody. I'm Manel Jerbi. I'm happy to share with you the results of our research paper entitled Malware Evolution and Detection Based on the Variable Precision RFSET Model. The goal of this paper is to highlight the useful aspects of malware detection systems and propose a novel method that deals with computer security threats. We will specifically focus on Android operating system. The outline of this paper is as follows. First, we start with the introduction. Then we give the problem statement and the objectives. Afterwards, we will show the proposed methods. Finally, we will conclude and give the future works. It's clear that the number of mobile system users is constantly growing, with Android leading the way. Usually those mobile systems deal with sensitive information, and that's why they are targeted by malicious intents. Malware programs currently represent the most serious threat to computer information systems, and they can take different forms of hostile software. Among those forms, we can refer to the obfuscated malware, which is known for their ability to disrupt and confuse the detection process. These facts led to call for efficient techniques to deal with these malware programs. Several approaches were proposed in the literature, and they can be categorized into three main heads: static approaches, dynamic approaches, and hybrid approaches. Static approaches are the most common ones used by antiviruses. They analyze the code without running it, and that's what makes them easily bypassed by obfuscated techniques. That's how dynamic approaches were proposed. They consider the behavior of malware during runtime, but they are also known for their greed on resources, which lowers the system's performance. Hybrid approaches were then introduced. They use both dynamic and static features, but it's shown that they can inherit both limitations from the previous approaches. Also, it was noted that all those proposed approaches can share a common limitation, which is the high dependency on the base of examples. So in our proposed work, we will focus on dynamic approaches, specifically those based on frequent API call sequences, also known as motifs or patterns, to deal with the obfuscated malware. So in order to detect efficiently the obfuscated malware, we need to diversify the base of examples, and that's why we propose a new detection method named ProRSDET, and which is based on evolutionary algorithms, bi-level optimization, and variable precision RFSET, and which comes with three main contributions. The first contribution generates artificial malicious motives relying on evolutionary algorithms in order to diversify the base of examples. The second contribution endorses the strengths of the detection rules using bi-level optimization. And the third contribution handles the possible inconsistency that may appear among the generated malicious motives. And we will use a variable precision RFSET model. So the bi-level optimization can be introduced as a special kind of optimization where two problems are in mutual competition. the outer problem or the outer task, also referred to as the first layer. Here we will use it to produce detection rules that try to their best to escape the malicious motives produced by the inner task or the lower level task. In fact, the lower level task produces artificial malicious motives, and specifically within this lower task or inner task, we need to make sure that the generated motives are reliable enough to be fed to the upper task to produce its detection rules. And that's how we called for the variable precision RFSet model introduced by Diarco as an extension of RFSet theory and can be considered as a mathematical tool to deal, among others, with the inconsistent information. In fact, inconsistent motives can share the same structure, but at the same time have different levels, which makes them considered as ambiguous motives. That is when we call for the variable precision RFSet notions, specifically the lower limit and the upper limit approximation, in order to keep only relevant motives. More specifically, in variable precision RFSet, we consider a set of objects characterized by a set of condition attributes and a decision attribute. Those objects may present some inconsistency. Variable precision RFSet, as previously mentioned, offers powerful mathematical tools, the upper limit and the lower limit approximations. On the one hand, the upper limit approximation represents a set of objects that can be possibly classified as belonging to a given concept with a precision level. On the other hand, the lower limit approximation represents a set of objects that can be certainly classified as belonging to a given concept with a precision level. So we can see the general overview of our detection method, which uses a hierarchical bi-level process that creates a competition between first two layers. In fact, the first layer presents the upper level and produces detection rules using a genetic programming based engine fed with the base of examples composed of malicious and benign motives, and also the outcome of the second layer, which is the generated artificial motives. This second layer is responsible of generating high quality malicious motives, relying on both GA-based engine that produces artificial malicious motives and a variable precision RFSet analyzer that aims to keep only the most reliable motives. So more precisely, in the first layer, detection rules are generated. A detection rule is a solution of the genetic programming algorithm and can be represented as a tree where the leaf nodes are API call sequences or motives, and the internal nodes are functions belonging to the connective set and or logical operators. This GP algorithm uses a fitness function to perform its generation task to generate detection rules, named F-outer, that uses a set of metrics which are the precision, the recall, and the percentage of the detected malicious motives. All those motives need to be maximized. Let's recall that the first layer's aim is to produce detection rules that try to their best to detect a set of malicious motives. For the crossover operator, new offsprings of rules are created for the new populations by exchanging randomly subtrees. And for the mutation operation, one new offspring is generated by randomly mutating a part of one selected GP tree. For example, the node AND can be mutated to the OR operator. The second layer first generates a set of malicious motives, a task done by the GA-based engine. Those motives will go through an inconsistency check processed by the variable precision rough set analyzer in order to keep only the most reliable ones. A task guaranteed by the variable precision rough set approximations. The GI-based engine assures all the steps required by a genetic algorithm, which are the evaluation, the selection, the crossover, and the mutation. Let us precise that a motif has a chromosome-like structure composed of succession of API call sequences described by its ID, its label, either malicious or benign, and its depth. To ensure its selection task, the GA uses a fitness function named finner and tries to maximize two metrics. The first one calculates the difference between the number of generated artificial malicious motives and the number of detected artificial malicious motives. And the second one guarantees the diversity of the artificial malicious motives. The crossover operator can be applied on parents having the same label, and the mutation operator is applied to the selected chromosome to maintain the genetic diversity. After generating these artificial malicious motives, the variable precision rough set analyzer is then applied. First, those generated patterns, which are none other than our set of objects, characterized by a succession of API calls, considered here as the condition attributes, and their corresponding nature is considered as the decision attribute. First, they will go through an inconsistency check to detect those with the same structure but with different labels. Then the variable precision rough set lower limit approximation is applied to keep only the certain malicious ones. Or the relevant ones. After that, the upper limit approximation is applied to help determine the set of motives that can be possibly classified as malicious ones. Finally, the ProRS detection process works as follows. So in order to predict the nature of a given app, first we will start by extracting its motives. We label them by comparison to the base of examples. Then we compare those motives to the antecedent of the detection rules in order to give the final classification result. In order order to perform our experimental analysis, we use different apps gathered from different state-of-the-art bases in order to form a final set of benign and malicious motives. And in order to assess RSTA'22, a comparison to a state-of-the-art method was performed, which is the AMD method, and where the following evolutionary parameters were applied. Also, we searched for the best combination of the variable precision rough set parameters according to the best registered evaluation metrics. To continue with our experimental analysis, and from the obtained results, when applying tenfold cross-validation, we can see that RSTA' outperformed various classifiers. Also, RSTA' was assessed using an unknown data set, which is the Draben data set, and it achieved better results than the state-of-the-art method, AMD. Also, we stick to show the number of the generated motives, where RSTA' succeeded to produce about 270,000 relevant motives. The same goes for the number of the generated rules, where RSTA' produced a respectable number of detection rules. Also, we can see that more than 51% of the possible generated motives have a relevance malicious index that is greater than 50%. Let's recall that the relevance malicious index is the ratio of the number of instances that belong to the possible set and having the same structure with the malicious label, and the number of the whole set of possible instances. The false positive and the false negative rates when compared to the state-of-the-art methods will give us an idea about the effect of the use of the bi-level optimization architecture endorsed by the variable precision rough set technique. Also, our method was assessed against known antiviruses, and it achieved a better accuracy rate. We used for that the Draben dataset as well. So, to conclude, we can say that the outstanding number of malware with a special mention to the obfuscated ones are still challenging to the detection systems, as they are mainly based on static bases of examples, which made the detection performance questionable, and that's how we came to propose a new detection method that relies on evolutionary algorithms and bi-level optimization and variable precision rough set model, and which showed its merits when compared to state-of-the-art methods. And as future work, we propose to increase the diversity of the usage features, to design adaptive parameter tuning strategy to improve the execution time, investigate other theories to handle data imperfections, and finally generalize our results to other operating systems. And thank you for your attention.
Thank you very much for nice presentation. And now it's time for questions. Please raise your virtual hand or write the question in the chat. I can't see the hands, but I have the question. My question is how the optimal parameters of models were.
How
you obtain
Sorry,
your
I can't hear you.
how you obtain your optimal parameters in your models?
By trial and error methods. So we tried different values for our parameters, and we took the best registered ones by trial.
Okay, the exemplary parameters alpha and beta. Okay, thanks a lot. And the second question is how you evaluate the results and split data to experimental part?
In the experimental analysis, we used different metrics, and we compared our results to the most recent state-of-the-art methods using those evaluation metrics with a common data set, which is the Draven data set.
I think Piotr is referring to the splitting between training, validation, and testing, Piotr, right?
Yes, right.
Yes, so if I've used cross-validation or something.
For the 10 cross validation, we used about 90% of the data set to train our model, and 10% to assess it.
And 10 cross-validation here, as mentioned in the caption of the table.
Okay, thank you very much.